Let's move to the final talk in this session. The Professor Yusuke Morisawa will give a talk about investigation of the electronic states of water in hydrate-melt. So please.
Thank you for kind introduction, Morita Sensei. And I'd like to thank Professor Tsenkoba and committee of this conference for inviting me to this conference. I'm Yusuke Morisawa from Kindai University. Topic of this talk is electronic states of water in highly concentrated aqueous solution observed by ATR for ultraviolet spectroscopy. I'd like to acknowledge thanks to my coworkers, Dr. Ikehata, Dr. Higashi, and Professor Ozaki, first developed ATR-FB spectroscopy, which is main topic of this talk. And Dr. Goto contributed very much for application of water research. And Dr. Nami Ueno, who was a student in Kindai University, carried out the experiment and analysis of this topic. Here I introduce a brief description for FUV spectroscopy. In the FUV region, all molecules have allowed electronic transition whose molecular absorption coefficients are 10 to the 5th per molar per centimeter. This transition includes not only a valence electron transition, but also molecular Rydberg transition. And such as N3S Rydberg or N3P Rydberg and so on. The first electronic transition of water are observed in FUV region. Here are contents of this talk. I'd like to start from the introduction for FUV spectroscopy and of water with conventional method. Then the main topic of this talk is ATR-FUV spectroscopy. We have been developed attenuate total reflectance spectroscopy in the FUV region. Using ATR-FUV, I and coworker revealed a new insight about electronic state of water. In the last topic, we will introduce the student study of hydrate-melt, which is very high concentrated aqueous solution of lithium salt. FUV spectra of water vapor, liquid water, and ice have already been observed in 1960s by the Painter's group. As you can see in the spectra, epsilon of this transition is about the 400 per molar per centimeter minus 1 per centimeter. Thus, if one measures the AX transition of water by transmitter spectra, path length of measurement should be shorter than 50 nanometer. It's difficult to observe for liquid water. So Painter's group use reflectance spectroscopy. And some investigation conducted for temperature dependence in the Bante region. However, they could not observe peak region because the reflectance spectroscopy suffer from the vapor of water. So they use the conventional the cell method. So they cannot measure the peak region. So thus they cannot determine whether the change tail region is from the shift or broadening of the band. Here, ATR FEV spectra of the H2O and D2O, or this one is H2O and this one is for the D2O. Vertical axis is ATR absorbance derived this formula. As to both H2O and D2O, broad absorption feature were observed in the FEV region due to the first electronic transition of the water. And this energy shift originates from the effect of hydrogen bonding, especially on the non-bonding electron on the oxygen, because this transition is from the non-bonding electron of the oxygen. From theoretical calculation, the first electronic transition of water assigned to mixed state of the transition to Rydberg state and sigma star. Here are the results of the results of theory. First singlet B1 state. First singlet B1 state is almost flat, flat potential around OH stretching coordinate. The size of electronic distribution becomes smaller in OH bond cleavage. That means the near potential minima of ground state have feature of the Rydberg. On the other hand, the bond cleavage region show the feature of the sigma star orbital. So this transition is very interesting in the balanced Rydberg mixing. So Dr. Ikehata and Dr. Higashi and Professor Ozaki at first developed attenuate total reflectance spectroscopy in the far ultraviolet region. Here are feature of ATR. Here are feature of ATR technique. The signal to noise ratio of the ATR spectra is very good, and compared to the total reflection, compared to the interface reflection. And ATR spectra does not suffer from the vapor of the water. Why can we measure the absorption spectra by ATR technique? As people learned in the ATR-IR spectroscopy, the electric field from the surface of the IRE into the sample. The electric field called the evanescent waves. This evanescent wave interact with the molecule samples. The effective path length here can be estimated this formula, and from this formula, the interaction path length is about the wavelength of the incident light. So for far ultraviolet spectroscopy, this interaction path length is about the several tens nanometers. One of the most important points of developing ATR technique in far ultraviolet region is material of the IRE. IRE should be transparent in observed region and have high refractive indices in this FUV region. From the literature of optical property of material, Ikehata and Higashi finally found that sapphire and quartz can be used for the IRE for ATR FUV spectroscopy. Here is a schematic diagram of ATR FUV spectrometer. This part is FUV monochrometer with a D2 lamp as a light source. Here is a sample compartment. IRE here can perfectly separate the sample and light path. So we can measure the FUV light which goes through the N2 path, and simultaneously we can change the sample in outer space, in atmosphere. These are photos of ATR FUV spectrometer. Here is a monochrometer. Here is a sample compartment. This is inside of the sample compartment. And we can introduce a sample from here, from outside, and we can replace the sample without break the N2 page environment. So as to the investigation of aqueous solution, effect of metal cation is very interesting. Here are ATR FUV spectra for aqueous solution of 1 molar alkali metal nitrate. Then the band peak at around 155 nanometers correspond to the X transition of water. After analyzing the spectra, we found excitation energy of X transition of water in the aqueous solution of salt proportional to Gibbs energy of hydration of corresponding cation. So, from this result, the first electronic transition of water show the environment of hydrogen bonding state of the water. Let's move to the topic of aqueous solution named hydrate-melt. Hydrate-melt is a very high concentrated solution of mixed lithium salt. Professor Yamada of University of Tokyo reported that using the combination of the salt can make very high concentration aqueous solution. In this solution, water hydrate to lithium ion show very small hydrogen bonding environment. It should be very special environment for H2O, also in the viewpoint of the electronic state. So we observe the ATR FUV spectra of the mixed salt of the lithium TFSI, lithium BTR aqueous solution. Here are the ATR FUV spectra of pure water, and the these aqueous solutions. Pure water shows the L sigma star first electronic transitions of the water at 155 nanometer. At the aqueous solution, even they contain about the 50 molar in this solution. Electronic transition of water is totally different from bulk water. It is noted that the anion gives the absorption band in this region. The but the first electron transition of water should show very large blue shift. And after that, we will use the second derivative spectra of the ATR FUV spectra. Here is the example of the second derivative spectra. As to pure water, we found three peaks for the pure water. Then in hydrate-melt, the band or intermediate band is disappeared, and the two other bands are increased in shorter wavelength region. Here we discuss about origin of blue shift using TDD-UFT calculation. Dr. Goto calculated the transition energy of the first electronic transition of water in hydration shell. Here is a cation, metal cation, and water hydrate to the metal cation. According to these results, compared to the 161 nanometer of bulk water in first hydration, of bulk, water in first hydration shell shift to the 138 nanometer, and second shell of water observed at around the 150 nanometer in lithium hydration situation. So from the spectra of hydrate-melt, the spectral alternation from the bulk to the hydrate-melt give some information about the changes in electronic state of water in this aqueous solution. However, we should confirm the assignment of the water transition, and we have to confirm the effect of the anion and cation in this alternation of the change. And we consider the concentration dependence of the these aqueous solution, and we discuss about the changes in the hydrogen bonding in the hydrate-melt. So at first, we discuss about the isotope effect of the first electron transition of water, because the first electronic transition of H2O show blue shift by isotope effect. So if the observed band shows a similar isotope effect, the band can be assigned to the water absorption. So here is the result of the for the two band in the shorter wavelength region in the high concentrated solution of the these salts. Band at 150 and 153 in H2O shift to the 147 and 150 respectively. So this result supports the assignment of first electronic transition of water for this band. Here we discuss about the effect of the cation. And so this is a peak observed peak position for the lithium TFS, sodium TFS, and the potassium TFS. The lithium solution shows shorter wavelength shift in both 150 and 152 nanometer band. This result corresponds to the trend of the shift in the calculation. So here are the concentration dependence for the lithium TFSI aqueous solution and the lithium TFS aqueous solution. This band decrease of the absorbance much in the lithium TFS. This is because of the because TFS do not have an absorption in this region. And here is a second derivative spectra of these solutions. The band at 162 is decreased for both solutions, and 157 shows a blue shift to the shorter wavelength region. And the in this middle concentration region, the band at 152 is decreasing for the both solutions. Then at very high concentration region, the shorter wavelength region is relatively increased in a high concentration region. So this is a detailed analysis of the peak intensity and the peak shift. I don't have the time to skip this one, but we concluded that from this discussion, in lower concentration region with increased lithium salt, decrease bulk water, and increase second shell water. And then in the region of the X larger than 0.2, second shell water also decrease, and all the water stay in the first shell of the water. Here are the assignment of the first transition of the water in various Columbia environment. From bulk water, second shell water, increase 0.3 EV of the band gap. And first shell water increase more than 0.5 EV band gap. It reflects the electrochemical property such as index potential. Thank you for your attention.
Thanks, Professor Morisawa. So it's time to open the question discussion. Any question, comment? So, Professor Morisawa, I have a question. So, I want to ask you about that. How can I say? Can we obtain the information of interaction or structure from the electronic spectra compared to the vibrational spectra?
So the vibrational spectra gives the information about the OH stretching band. So the this information very sensitive for the hydrogen bonding as a proton donor. But the first electronic transition of the water is a transition from the non-bonding electron. So that this transition is sensitive for the Lewis base of the water.
From the viewpoint of the ion, can we get the information of the ions by the electronic spectroscopy?
So you mean the anion or cation? Anion? So
possibly, yeah.
So yeah, I'm honestly speaking that I cannot get the information of the anion because